All right. Hello, everybody. I hope you guys have been having a good week. Crazy that we've been out of school for so long, but hopefully we'll be able to get back together in the classroom again soon. I know that learning online for everyone is kind of difficult. So if people have questions or need any help, feel free to email me, as several of you have already been doing, and I'll be glad to get back to you as soon as I can and help however I can. But hopefully we'll be getting back to normal very soon. All right, so hopefully you can see my screen here. I'm looking at the homework on number 55 as a good review problem for our linear programming inequality stuff. So this would be 3.1 through 3.2. So we'll work this problem as a review, and then we're going to move on to 3.3, which is more linear programming, but this time it'll be sort of in word problem form. Okay, so question 55, your numbers might be a little bit different, but hopefully you can follow along and fill out your problem as well as we go. So the first thing to do here is to try to graph this system of inequalities. Once we graph the system of inequalities, we need to figure out what the feasible region is. And the question also asks us to tell if that region is bounded or unbounded. Once we have the feasible region, in the problems that we're going to do in 3.3, we're going to try to minimize or maximize some function in that region. Okay, but to get started, we need to put these equations in slope-intercept form so we can graph them. So I'm going to do that in the pane to the left. So let's see, the first equation, y minus 2x is less than or equal to 7. I'll just add that 2x over to the right side. So that means that y is going to be less than or equal to 2x plus 7. So that one's nice and easy. It's already in slope-intercept form. If we just ignore the less than or equal to part, that's a graph I can write down quite easily. The second equation is also nice, right? It's already in slope-intercept form. So instead of writing 3 minus x, I'll just change this around a little bit so it looks nicer as a negative x plus 3. Right, but that's already in linear form. And then we have our last two equations, which are the normal x and y must be positive. Okay, so that's our system of equations. And now we need to graph that system of equations. And let's see if we can't figure out what our region, our feasible region ought to be. Okay, I'm gonna have to actually scoot this down a little bit, since our y-intercept is 7 for the first equation. There we go. Hopefully that's enough room. All right, so first equation, it's got a slope of 2, right? 2x and a y-intercept of 7. So let's go ahead and graph that one. So I need to go, let's see, 1, 2, 3, 4, 5, 6, 7 up. That's our y-intercept. And then a slope of 2. So it goes over 1 up 2. So the line looks something like this. Get rid of that. There we go. That's our first line. The second line is negative x plus 3. So that's a y-intercept of 1, 2, 3. And then a slope of negative 1. So we go over 1 and down 1. The line that looks like this. And then the last two equations really are just the x and y axes respectively. Okay, so let me extend this line a little bit. There we go. So already it looks like our region is not going to be bounded, right? There is like this triangle right here, but that triangle is behind the y-axis, which means that in this triangle, our x coordinates are negative, right? So that goes against the x greater than or equal to 0 equation already, which is not great. But let's take a look at the inequalities and see what we can fill out. The first equation says that we're looking for points whose y coordinate is less than or equal to the points on the line 2x plus 7. That's this line up here. So points who have a y coordinate that's less than or equal to that line are points below it. So this way. If I look at the second equation, right, we're looking for points whose y coordinate is bigger than that line. So we would shade up this way. And then, of course, I have to stay within the x and y axes with this third equation. Okay, so this feasible region is certainly unbounded. It's unbounded both in the y direction, right? I can go as far up as I want, and it's also unbounded in the x direction. I can go as far to the right as I want. So not great for trying to, for instance, maximize an objective function. But let's see what the rest of this question says. Okay, so I guess we got to put these on the graph. Let's see, so I need a line. This one was a slope of 2. Let's see, we go up by 2s. All right, let's just make sure that's correct. Yeah, because the scale is just by 1s on this one. I hate the graphing tool on this. I guess you guys probably do too. Okay, and then the second equation had a y-intercept of, let's see, 3. That's right here. And it's got a slope of -1. Like that. Both of those lines are solid because they are less than or equal to or greater than or equal to. And then lastly, we have the axes. So let's see, I think that's right here. And right here. Both of those are still not strict inequalities, so solid lines. And then let me save this. So are we supposed to fill this in? Let's see, to graph the system. Probably, yeah. So fill in right here. There we go. That's the picture I had before. Save, check, perfect. So just watch the, whether you need a dotted or solid line, and then you need to watch which way those inequalities go, and you'll be just fine. I'm sorry for the clunky software, but hopefully it'll work okay. All right, and we said the region is unbounded. Okay, so that's it for this question. So in some of the other questions, you might be asked to maximize or minimize a quantity, and that's what we're going to do next in these word problems. So without further ado, let's skip ahead to chapter 3.3. I'm going to go ahead and close this. I'm going to stop sharing for just a second so I can share only the notebook here. It'll look a little nicer. All right. There we go. Okay. So this time I wisened up and I wrote down the word problems beforehand, so I didn't have to write them all out and you guys just sit there watching me write a novel, right? Okay, so here's the first question. This is also a question from your homework. Again, you might have some different numbers, and it's written in a little bit of a different way in the homework, but it should be the same to solve this problem. Okay, so we've got a company producing handmade shawls and afghans. They do 3 things to prepare the shawls and afghans. They spin the yarn, dye it, and then they weave it. A shawl requires 1 hour of spinning, 1 hour of dyeing, and 1 hour of weaving. An afghan requires 1 hour of spinning, 4 hours of dyeing, and 2 hours of weaving. And here they're giving us some constraints. So there are at most 7 hours available each day for spinning, 18 for dyeing, and 10 hours for weaving. And then here's the actual question. If the company sells each shawl for 10 and each afghan for $23, what is their maximum profit? and at what production rates. Okay, so like we've done before, the first thing we need to do is to identify the variables, the objective function, and then the constraints. So I can already see the objective function from the question. It asks, how many shawls and afghans do we need to maximize profit? So our objective in this question is to maximize profit, right? And then, so our constraints are going to be, the rest of the problem, but we need to figure out what is going to be the equation for profit, and then what are our variables going to be. And so the variables, you get a clue right here, what those should be. They are the number of hours. So production rates, we're looking for the, I'm sorry, not the number of hours, the number of shawls and afghans will be our variables. So I'm not sure what they mean by production rates. Well, I guess we'll get there when we get there. Okay, so objective is to maximize profits, and then variables is going to be the number of afghans. Let's do this in order. So they say the number of shawls first. Number of shawls, I'm going to call that X. And number of afghans, I will call that Y. Okay, and since those are our variables, we can now come up with the objective function. We know that we get $10 for each afghan, and we get $23, I'm sorry, for each shawl, and $23 for each afghan. So 10 times the number of shawls plus 23 times the number of afghans is what we're trying to maximize. So I'll just call this Z, right? We want Z to be as big as possible to maximize our profit. Okay, so let's write down some constraints now. Let's see. So the constraints, what you're looking for are statements like there are at most, or at least, or cannot be any more than. So phrases like that. So the first thing we know is there are at most 7 hours a day available for spinning. Okay, so that means since one shawl requires 1 hour of spinning, then we have 1 times the number of shawls. And then let's see, how many hours do we need for afghans? An afghan requires 1 hour of spinning as well. So 1 times the number of afghans. That should give us the total number of hours for spinning for the shawls and afghans put together. And we're told that we only have 7 hours available. So this should be less than or equal to 7. Right, so the number of hours for shawls plus the number of hours for afghans for spinning has to be less than or equal to 7. So it can be equal to, because there's at most 7 hours available, but it can't be any more than that. Okay, so that's the first one. The second one here says that there are at most 18 hours for dyeing. So we're going to do the same thing. For dyeing a shawl, that requires 1 hour. So we've got 1 hour times the number of shawls. Dyeing an afghan requires, let's see, 4 hours. So we have plus 4 times the number of afghans. And that's got to be less than or equal to the allotted hours for dyeing, which was 18. Okay, and then lastly, we have 10 hours for weaving. 10 hours for weaving, there we go. So that means that, let's see, a shawl requires 1 hour of weaving. So we have 1 times the number of shawls. And then an afghan requires, let's see, 2 hours of weaving. So 2 times the number of afghans. And that ought to be less than or equal to our allotted 10 hours. Okay, and then lastly, you could make the case that, well, we certainly can't have a negative number of shawls and Afghans, so X and Y ought to be greater than or equal to 0. So that's sort of the given constraint. Okay, so once we have all our constraints down, we know what our objective function is, we know what our variables are. The next thing we need to do is to create our feasible region, and then we're going to try to maximize the variable z in that feasible region. So to create the feasible region, we need to graph all of these inequalities, which means it would be nice if they were all in slope-intercept form. So that's what I'll do next. So for our top equation, all I need to do is subtract x to the other side. The second equation, I'll have to subtract x and then divide by 4. So let's see, that'll give me negative 1 over 4x. And then 18 divided by 4, what's going to be 9 halves, right, I guess? All right, and then on my third equation, I'll subtract x and divide by 2. Let's see, so that gives me negative 1/2 x. And then 10 divided by 2 is 5, so I've got a plus 5. And then my other two equations are already in the correct form. Okay, so those are the equations that I'm dealing with. Now what I'm going to do is take these over to Desmos. So you can certainly use Desmos if you have your computer with you, but it's always nice to practice this on your calculator as well. I would do it on the calculator, but I don't have that today. So try to graph these on your calculator, but I will do so in Desmos. Let me stop here and share. Well, hang on here. Green. Okay, let's put those equations in. So we've got y, and I'm just going to use an equal sign, not the inequality, because all the shading just gets to be too confusing. And I would suggest the same thing on your calculator, right? If you try to use the inequalities, even if not all the calculators have that function, but if you try to use all the inequalities, it's going to get really complicated really fast. You won't even be able to see the lines. So this is the easier way to do that. 1/2 plus 5. All right, and then we've got our normal x equals 0, y equals 0. So that's just the x and y axes, respectively. Looks like we've got a couple regions that could be what we're looking for, but let's make sure. Okay, so our top equation, that was y is less than or equal to negative x plus 7. So if I briefly make this a less than or equal to, you can see I need to be to the left of this red line. Okay. The second equation was a less than or equal to. So I also need to be to the left of the blue line, the left of the red one, left of the blue one. And then finally, our third equation is a less than or equal to once more. Or equal to. So that means I need to be below this green line as well. Okay, so if I'm below all three of these lines, of course, I have to be to the right of the y-axis and above the x-axis as well because of these last two equations. That means I'm in this sort of final inner almost triangle region. Let me turn off that shading. All right, so my feasible region is the one with these corner points here. If I can turn them on. Right, that's my feasible region. And I'm thinking 0, 0 is probably not going to be a solution, but you never know. Okay, So let's now write down all of those points, and then we're going to try to maximize our objective function using those corner points, right? So we're using right now the fact that we know if our feasible region is bounded, which in this case it is, that when a maximum or a minimum exists, it'll be at one of those intersection points. So we just have to check all of them and see which one maximizes our objective function. Okay, so bear with me here. I'm going to create a new page to my notebook, and then we'll go over there. There we go. All right, so the points we're going to check. We've got 0, 4.5, 2, 4, 4, 3, and 7, 0. And then the origin was in there too, so we'll put that here as well. And then again, we're trying to maximize. Let's see, what was it? We're trying to maximize the objective function, which was 10x plus 23y is equal to z. Let's see, 10x 23y equals z. All right, so all we got to do is now plug in all these numbers and see what we get. So let's plug in the first one. I've got 10 times 0 plus 23 times 4.5. That is equal to, let me grab my calculator here, which is my phone. I should have had my calculator pulled up already, but that's all right. So 23 times 4.5, 103.5. All right, that's our first one. Let's check 2, 4. So we've got 10 times 2 plus 23 times 4. So that's 20 plus, what would that be? 46 times 2, 92. So 112, so a little bigger. Let's check 7, 0. 10 times 7 plus 23 times 0. That's going to be 70, so that's definitely not the winner. And, oh, I forgot 4, 3. Let's check that one as well. All right, so 10 times 4 plus 23 times 3. That is 40 plus, well, let me do this on the calculator. I don't trust myself. 40 plus 69, that is 109. So still not beating our 112 here. And then lastly, 0, 0 is not going to be it, right? Okay, that is a minimum value, right? But we are trying to maximize our function, so we don't really care. All right, so this second equation here is the winner. So 2, 4 is the coordinate pair we're looking for. So the number of shawls ought to be 2, and the number of Afghans ought to be 4. Okay, and then the question asks, what is going to be the maximum profit? That's the output here, 112. All right, so that's how to do one of these word problems. Now I'm going to get into a little bit more of a complicated one, but I hope that's a good introduction. And then let's try another one. Okay, here we go. So this time we have a manufacturing company that receives orders for engines from 2 assembly plants. Plant A needs at least 45. plant B needs at least 32 engines. So these look like they're all constraints, right? When I see the words at least or at most, right, I'm thinking that's probably going to be a constraint. So just keep that at the back of your mind. So the company can send at most 120 engines to these assembly plants. It gives us the cost per engine to ship to plant A, and then the cost per engine to ship to plant B. Let's see, plant A gives some rebates, and so does plant B. And the manufacturer estimates they need at least $1,500. So again, that's going to be a constraint, right? Because I see that at least statement. Okay, so here's the question. How many engines should be shipped to each plant to minimize shipping costs? All right, and we're going to use the same steps here. So the first thing we want to do is figure out what the objective function is, figure out what the variables are, and then we'll look at the constraints. Okay, so the question asks, first of all, how many engines should be shipped? So the variables we're looking for is the number of engines shipped to, so it's how many engines should be shipped to each plant, right? So the first variable will be the number of engines shipped to plant A. And then the second variable will be the number of engines shipped to plant B. And I'll call the first one X and the first one Y, right? Use whatever variable letters you want, but that just kind of keeps us consistent. Okay, that's my variables. Let's look at the objective of this problem. So the objective is right here. That's to minimize the shipping costs. And let's see if we can come up with a function that would do that, or that would give us the shipping cost, right? A function that we can minimize. Let's see. So the problem tells us it takes $35 per engine to ship to plant A and $40 per engine to ship to plant B. Let me erase the other stuff here. I'm sure that's getting confusing. Okay, so that's our shipping costs, right? So we've got 35 times the number of engines we're shipping to plant A, that's X, plus 40 times the number of engines we're shipping to plant B, that's Y. And that's going to equal our total shipping cost, which I'm going to call Z, right? And that's usually the function we want to minimize or maximize. All right, and the last thing to do is to find the constraints. And then we just have to apply the same stuff we've been doing all this time. Okay, so we're looking for those at most or at least statements. The first one I see is right here. Plant A needs at least 45 engines. So that means that X, which is the number of engines shipped to plant A, has to be at least 45. So plant A would be happy if it were bigger than 45. They'd still be happy if it were equal to 45, but it can't be any less than that. So that's why I picked a greater than or equal to there. The second at most or at least statement I see is right here, and it says plant B needs at least 32 engines. So same sort of thing. The number of engines shipped to plant B ought to be bigger than or equal to 32. All right, so far so good. Let's see, here's another statement in the next sentence. The company can send at most 120 engines to these assembly plants. So in total, the number of engines shipped to plant A plus the number of engines shipped to plant B has to be less than or equal to 120. So they can ship less than 120. They can still ship 120, but they can't ship more than that. So that's why I'm picking less than or equal to in this case. Okay, and the next sentence gives us our cost functions. We don't care about that anymore. Let's see. So there's some stuff about rebates, right? So plant A gives $20 in rebates. Plant B gives $10 in rebates. And then we have our final constraint. The manufacturer estimates that they need at least $1,500 in rebates, right? So the number of rebates that plant A gives, which is $20 times the number of engines shipped to plant A, plus the number of rebates that plant B gives, that was $10 times the number of engines shipped to plant B. That needs to be at least $1,500. So it could be bigger than, it could be equal to, but it can't be less than $1,500. So that's our last constraint. Of course, you can always say that, well, X and Y need to be bigger than or equal to 0, right? You can't have a negative number of engines shipped. But if you look at our first two constraints here, those first two constraints already tell us that X and Y are going to be positive. So we really don't even need this bottom one. You can certainly have it. It won't give you any wrong answers, but we don't really need it for this problem. Okay, the next step is to get all of these in y-intercept form, and then we'll graph them, find our feasible region, and go from there. Okay, so I probably need to like add another page or something in order to do this. Oh, you know what? I'll just do it at the top of the page. Okay, so let's see. Two of these equations are already fine. So x greater than or equal to 45, y greater than or equal to 32. Those are already in the right form. The next equation, x plus y is less than or equal to 120. I'm just going to subtract x to the other side. So y will be less than or equal to negative x plus 120. And then the last equation, 20x plus 10y is bigger than 15,000, or sorry, 1,500. I need to subtract that 20x to the right-hand side and divide by 10. So I will end up with y is bigger than or equal to, I've got negative 2x, right? 20 divided by 10 gives me the 2. And then plus 150, right? Because 1,500 divided by 10 gives me 150. And those are my constraints that I'm now going to graph. So bear with me. Let's switch over to Desmos here. Okay, I'm just going to erase our earlier equations. And let's plug in the ones we just found. Again, I'm just going to use equal signs. Right, just, whoop, that one should be y. Okay, negative x plus 120. And then lastly, negative 2x plus 150. All right, well, if you look over to the right, we can't see anything. So I'm going to make this a little smaller. There we go. So now I can see what's going on. Well, I make it a little bigger. There we go. So I can sort of see all the intersections now, right? And we can kind of think about what the region ought to be. All right, well, first of all, I know that x is going to be bigger than 45, y is going to be bigger than 32. That's the red line right here and the blue line right here. So we just have to be to the right of that red line and above the blue line. Right, so just kind of think about this as our new axes almost, and we need to be sort of on the right side of that. Okay, and then here's the two equations we're really concerned about. The green line right here, y is supposed to be less than or equal to this green line. So that means we should be below the green line, right? We're looking for y coordinates that are less than those on the green line. So we're going to be below there. And then the purple line, y is supposed to be bigger than or equal to this purple line. Let's see this guy right here. So we should be above the purple line. So in between the green and purple lines, we're in this sort of quadrilateral shape thing. I don't think that's technically a quadrilateral anyway. A shape with 4 sides. All right. So I'm just going to label the corners. They won't stay labeled, of course. Oh my goodness. There we go. Okay, those are the corners we need to check, right? And this time we are checking for a minimum, right? We're trying to minimize shipping cost. So again, I'm going to take us back over to the notebook. We'll check our shipping cost for each of these corner places and see if there's a smallest value. Okay, and we'll probably need a new page this time. Here we go. Okay, so let me just write down those coordinate pairs real quick for you. So we've got 45, 75, 88, 32, 59, 32, and then lastly, 45, 60. All right, so those are the coordinates that we need to check. And again, the function that we're trying to minimize, if I go back here, that is down at the bottom, this guy right here. So 5x plus 40y. Okay, so let's plug these guys in. So we've got 5 times 45 plus 40 times 75. Let's see, that is 40 times 75. 3,225. Okay, next I've got 5 times 88 plus 40 times 32. And let's see, 5 times 88 plus 40 times 32. That is 1720. Okay, 5 times 59 plus 40 times 32. Let's see, 5 times 59 plus 40 times 32. That is 1575. And then lastly, we have 5 times 45 plus 40 times 60 plus 40 times 60. And that gives us 2625. Okay, and we are trying to minimize z. So I'm going to pick the equation that has the smallest value. That is 1575. So that means our coordinate pair 5932 is the winner. So the number of engines shipped to plant A ought to be, let's see, 59. And then the number of engines shipped to plant B ought to be 32. And our shipping cost is the number that we just minimized. That's 1575. Okay, so this is probably the solution. Let's look back at the problem and see if we missed anything. But I think that's all they asked for. Right, so they just asked for what is the minimum shipping cost, and let's see how many engines should be shipped. So we have answered that question. Okay, so they shouldn't get any worse than this, right? Most of the questions will look very similar to this. You might have some charts that are a little bit difficult to read, but if you have problems, feel free to email me, come by office hours. Hopefully we'll be back on campus soon. And just let me know and I'll be glad to help. Otherwise, have a great rest of your Thursday, and I will see you guys next week.